Well, hello again, and in this series of videos, what I'd like to do is just show a few of the new features that are included in the 2017 version of solidThinking Embed Digital Power Designer. The first thing that I'll show in this video is the new frequency analysis on a model-based type. So what we have here is a new block which we can find in the digital power tool section under frequency response analysis and the model-based frequency analyzer. Okay, so we can cancel this one now. What we can see here is what we're going to do is we're going to start a frequency analysis from time equals 0 up to 20% of the total simulation time. So looking at the simulation time here, we're going to be running at 50 megahertz here, since the buck converter is going to be switching at 500 kilohertz. So we'll multiply that by 100, we'll have a good simulation. We go here and we're going to be running for 10 milliseconds. Sorry, so 20% of 10 milliseconds would be the first 2 milliseconds. Here up to here we'll run the frequency analysis. After that we'll let it go and we'll do a time domain analysis on exactly the same simulation diagram. So let's click go and off we go. Now what we're doing here is basically controlling a buck converter with a type 3 compensator, okay, in voltage mode control. We're going through here, we can click inside here and we can see the frequency response being generated over this given time. And we're past 2 milliseconds now, and we know that the frequency response analysis is finished. We'll have a look at that later. We'll let this simulation go, and now we're going to do some transients. We just dropped off the load. It was important during the frequency analysis part that we kept everything stable, and this is what we did with the load constant here. After 3 milliseconds we did the first transient, and after another 6 milliseconds we'll put the load back on again. Okay, so we'll run it up to 6 milliseconds. Here we have our input voltage transient, which we can see here. Amplitude slew rate, which is 4.5 milliseconds, and 5.5 milliseconds it will return to the nominal input voltage. We can look at that bigger. Okay, no problem. We can zoom in, no problem. Zoom in on the output voltage there with the output voltage ripple. Okay, this is the input voltage in the light blue, the load current in the pink color, where we drop the load down here, dropped it back up, put it back up again. The yellow is the input current, okay, and the green is the modulation signal coming from the compensator. We can bring this down. We've also graphed the ramp PWM generation here. Okay, this is the PWM and this is the modulation signal again. Now, okay, we can let this finish. Have a simulation. Now, what is new is in all the frequency blocks we have a frequency input in all the normal simulation blocks we have a frequency input in each one of these here. So we can double click in this. We have a frequency response of the input divider, which cuts off around the 20 kilohertz mark here, and this is determined by the capacitor and the resistor here. Okay, same thing for the compensator. One easy way to go through it is we can use the F2, okay, and we can just cycle through that. This is the type 3 compensator response, the voltage mode control response, okay, the buck converter response itself in continuous conduction mode, of course, and these are inside the frequency loop, which just come here inside the frequency block, these plots have been determined. We determined here the plots. We said what we wanted to plot. We wanted to plot the open loop response, the converter response of the buck converter, and the compensator response, and also the Nyquist response. And to see the Nyquist, we just click inside the Nyquist, and we've got the Nyquist response, and we can see the light blue line here, which is giving us a stability margin. Okay, so here we have in the green the compensator response. Yes, okay. The open loop response, total open loop response is in the yellow, and the converter response, the buck converter, is in blue. We can see the closed loop response here. Okay, you can see the output impedance of the buck converter, both as an open loop and closed loop output impedance, and we get the input to output attenuation as well. Okay, so these are some of the basic features of the new model-based frequency analysis, which can be seen by doing normal simulation. You can do it in at the same time that you do the normal time domain simulation. So hope that was helpful, and thank you for listening.